Alright, so problem number 4 on the test is going to be kind of a combination of velocity and acceleration. So the first part, determine the angular velocity or determine some velocities, the magnitude of velocity of point C. The next part, determine the angular acceleration or some accelerations of some points. So, for the first part of a problem like this, you can use either the relative velocity method or instantaneous center of zero velocity method. You can choose which one you want to use. Now, the main thing we're using one of those methods is because this bar, there's going to be a bar that's not in pure rotation. A bar that's kind of linked on one side, linked on another. A bar it's not just fixed. It's not fixed about point B, rotating about point. It's not fixed about point C. And so for bars that are not in pure rotation or pure translation, got to use one of our methods that we kind of looked at and earlier this semester. So let's see. I think I'm going to use a relative velocity method, but real quickly, let me just see where the instantaneous center would have been. All right, so if this is going to the left because of that, this is going up here because of that. So here, my instantaneous center would have been way down here, and that probably would have been pretty easy. It's a right triangle. If that's 60 degrees, this is 60 degrees, 30 degrees. This length right here, that wouldn't be too bad. But I'm gonna follow the way I did this previous semester. I'm gonna use the relative velocity method. So personally, sometimes I think the instantaneous center of zero velocity method, the math's a little bit easier if you can visualize that triangle. If you can't visualize that triangle, if you can't get the angles of that triangle very easily, then instantaneous center might be a little bit hard. But if you can see the triangle, and if it's a right triangle, or if you can use law of sines pretty quickly and easily, the math is pretty easy. Now, though, one benefit to doing relative velocity is later on down here, you're going to have to do relative acceleration, and so you're kind of in the same mindset doing your cross products. You can probably reuse that R, if you're doing R, B slash C, or C slash B, or something like that, then you might reuse the R. So, I don't know which method is going to be easier for you to do. If for some reason you have time, you can try both of them to double check that you get your answer. Correct for the velocity method. The velocity method, you have two options: relative velocity or instantaneous. All right, I'm going to use relative velocity, and so I tend to kind of. All right, I think I know the most stuff about what B is doing, so I'm going to put C over here. VC equals VB plus VC slash B, and this is a relative term. This velocity of B, the velocity of C with respect to B. That's the velocity of C if B was your reference reference point. This is omega cross R C slash B, and that's the R from B to C. All right. So I don't know the velocity of C, but do I know what angle it's going at? Do I know its direction? All right, let's think about this. The velocity of C has to be going along this direction, right? Because of this link right here, the velocity is tangent to that direction, tangent to that link. Now, it's either going this way or this way. You can choose whichever one. If your answer comes out negative, that was correct. Sometimes you can visualize it. If this velocity B is going that way, which way do you think velocity of C is going? All right. Now, what direction is that? What direction did I just draw that? At what angle did I just draw that? This pink line is 60 degrees from horizontal, right? This velocity is perpendicular to that. It's going to be 60 degrees from vertical. All right, so this VC right here, I'm going to write as VC sine 60 in the negative I. So negative VC sine 60 in the I. Positive, because it's going up, cosine 60 in the J. And that's my VC. Do you see that you need to go ahead and get the direction of that, so that you only have one unknown, the magnitude right there. All right, VB. Do I know it? Yeah, I think I know it, because, and not looking at what it's attached to, but looking at this disc right here that is rotating at 6 radians per second. What velocity does that make that? VB equals R omega, 0.36. It's 1.8, and if this is going that direction, this would be perfectly in the negative I direction. I've got to get that negative I myself. I've got to visualize that myself. And, we're lucky that it was just on the very bottom of a wheel that is spinning right here. Okay, so VB is negative 1.8 in the I plus omega. Omega, I don't know, but I'm going to say it's in the K direction, right? Because this is a two-dimensional problem, and angular information for things that are in the XY plane is clockwise or counterclockwise, and we say counterclockwise is positive K, clockwise is negative K. I'm just going to assume it's positive K. Again, if my answer comes out negative, then then I chose the wrong direction. All right, then I need an R of C/B, which is from B to C. From B to C, 1.5 in the I. 1.5 in the I. All right, so that one equation has two unknowns, VC and omega of CB. So that's fine. If you get that one equation and it's got three unknowns, you did something wrong. If that one equation, honestly, if that one equation has one unknown, probably did something wrong. Generally, we're going to have two unknowns, an I and a J equation we can solve for those two unknowns. So my I equation, negative VC sine 60, is on the left-hand side. On the right-hand side, negative 1.8. All right, that right there, though, that's not going to be in my I equation, is it? It's going to be in my J equation. So this one equation only has one unknown. VC equals 2.08 meters per second. Came out positive, which means I just chose the right direction. It was going that way instead of going that way. And my J equation, VC cosine 60 equals, all right, so here, this is going to be in the J, so 1.5 omega. But should this be positive J or negative J? K cross I. I like to do this circle type thing. If I'm going kind of in alphabetical order, I cross J is positive K. J cross K, positive I. K cross I, positive J. So yeah, there just said it. K cross I is positive J, and there's positives, positives, positives. It's positive right here. Plug in this 2.08 right there, and get omega CB is positive 0.69 radians per second. Positive means I chose correctly. I chose K. This is counterclockwise. Positive K. Okay, so that was getting the velocity and angular velocity using the relative velocity method for bar BC, right? No need to use relative velocity method for bar AB. For bar AB, I can find the velocity of B, negative 1.8 I. For bar CD, I can, find, I know the direction for point C. Now, sometimes it might ask us to take this velocity of C and find the angular velocity of this bar, omega CD, right here. V equals R omega. So I would look at that link knowing that VC is 2.08 and the R is 0.6. I can find the omega of that bar. But, if it doesn't ask for something, don't try to answer it, I guess. Okay, that was the velocity, half the problem. And I needed to do that first because I'm going to take this angular velocity into my acceleration half of the problem, my acceleration part of the problem. Okay. All right, so we did that. Now we're going to calculate the angular acceleration of bar BC and the angular acceleration of bar CD. Now, we may have done this problem before, but it's good to redo it. I'm not sure if we've done this exact problem. This is rotating at a constant angular velocity of 6. So what does that make this alpha of a 0? Makes that alpha of a 0. So that's an important point. Because many times it'll say, hey, okay, the angular velocity is 6, the angular acceleration is something. But here it says the angular velocity is 6, the angular acceleration is 0, because it's a constant angular velocity. All right, anyway, let's get on to part B. Let's calculate the angular acceleration of bar BC and angular acceleration of bar CD, both as Cartesian vectors. So I only have one method, the relative acceleration method. So let me kind of set that up. Something like acceleration of C equals acceleration of B plus a C slash B. And this one I rewrite as not only alpha cross R, but also minus omega squared times R. This R is RC slash B, RC slash B, alpha of CB, omega of CB. And that right there is what I needed right there, and I'm going to plug that in for omega squared. Next thing I like to do is make a note of this point B and point C. Are those linear or normal tangential? Point B is normal tangential, right? Because of what it's connected to. And that disk is traveling in a circular path, so don't forget about the normal acceleration in addition to the tangential acceleration. Also, point C is normal tangential. So let's think about both of those. AC normal, AC tangential. AB normal, AB tangential. Which one do we want to start with? Let's start with C. So I kind of like to come over here. This is kind of a side note. So I'm not looking at the whole equation. I'm not looking at the main bar BC. I'm looking at C being connected to this bar CD right here. All right, so because looking at link CD, let's think about AC normal and AC tangential. AC normal excuse me, sorry. All right, AC normal is either R omega squared or V squared over R. Again, I'm looking at link CD, so this is R of CD, omega of CD. But I didn't calculate that. I think that was what I was talking about at the very end. We could have used the 2.08 and calculated that omega of that bar, but I didn't. But I do have the velocity, 2.08. So this is 2.08 squared over 0.6. All right, that is 7.21. But is that in I? Is that in J? Oh, this is going to be tough. Normal is into the curve. This is into that 60 degree at that angle. At this, where's my 60 degree angle? 60 degrees would be right here. At 60 degrees angle. At 60 degrees. Let me give me a little bit more room. Okay, so this, written in I and J, in the I direction, 7.21 cosine 60 in the negative I, and down 7.21 sine 60 in the J. That was a tough one, and that was just a little bitty part. That's just that term is going to be, let me get some numbers. Negative 3.61 in the I, negative 6.24 in the J. That is what I'm going to plug in just for that term right there. All right. AC tangential is our alpha of CD. All right. This is going to be 0.6 alpha of CD, which is what it is asking for. It didn't tell us anything about alpha. It didn't say it's 0. We're not going to assume anything. That is one of the questions that we're asking, the angular acceleration of bar CD. And so this one again is at, it's not in I, not in J, it's at some angle. If it's going that way, it's going to be at kind of this same angle, this sine 60 in the I, cosine 60 in the J. Also, it's going to be opposite what I just did right here, because the tangential acceleration is not the same direction as the normal acceleration. So it should not look similarly to what you did here with your sines and cosines. It's perpendicular. It's going to be opposite that. In fact, let's give it a direction. If the normal, that link, and that normal acceleration is 60 degrees from horizontal, this is going to be 60 degrees from vertical. All right, 0.6 alpha CD sine 60 in the negative I, and up 0.6 cosine 60 in the I. And if you like to do what I like to do, give me some decimal places, maybe more than just 2, but maybe this rounds 0.520. Alpha CD in the I, and positive 0.3 alpha CD. Let's see, this one is J, sorry. Yeah, this one is J. That one is I. All right, and so that is what I'm going to plug in just for this little term right here for my tangential. Okay, now let's take a side note and look at point B. So look at point B on that wheel, that disc AB. Right on that disc A. AB normal and AB tangential. AB normal is r omega squared, or v squared over r. I think I've got the r and the omega squared. I'm only looking at wheel AB. All right, 0.36 squared, 10.8. Okay, but is this I, is this J, is this at some angle? We were lucky that this was just at the bottom of that disc. It is into the curve, which would be completely all in the positive J. So this is in the positive J. AB tangential is R alpha. That is 0 because it said it had a constant angular velocity. Constant velocity means acceleration is 0. Okay, but only the tangential acceleration is 0. It still does have some normal acceleration. Anytime something's in a circular path, don't forget about normal acceleration. All right, so that right there is what I'm going to plug in. Right there for that term. And that term is 0. Okay, now I think I'm ready, because I don't know that one. I'm going to plug it as an alpha K, but I do know all 3 of those other things. So let me go to the main event, right? Let's plug in to our acceleration equation right here. Okay? Alright, so let's plug in. Alright, so on the left-hand side of my equation, I've got AC, which has normal and tangential, and both normal and tangential are both at some weird angles. So this is negative 3.61 in the I minus 6.24 in the J, 0.52 alpha CD in the I plus 0.3 alpha CD in the J. That's what I've got on the left-hand side of my equation. On the right-hand side of my equation, the next thing is AB. AB normal and tangential, but tangential was 0. Normal was 10.8 in the J, plus alpha BC in the K direction, crossed with R, which is 1.5 in the I. This is R from B to C. From B to C. Minus omega squared. That's that 0.69 that I needed from that other equation. I mean, the first half of the problem. Times 1.5 in the I. Remember, this is just times. This is a cross product. All right, there we go. That is the major part. That's what I'm going to be looking for. I'm going to try to find that equation on your formula sheet. and see how accurate that is. The rest of it is just math, which I do want you to do. All right. My I equation would be negative 3.61 in the I minus 0.52 alpha CD. What do I have on the right-hand side? All right, that's in the J. That K cross I, that's not going to show up in my I equation. The K cross I is going to show up in my J equation. But this one right here, negative 0.69 squared times 1.5, that is in my I equation. This only has one unknown, so I would solve immediately for this and get alpha CD equals, it's running off the page. I don't have it with me. I'll come back and circle back to that, give that to you. All right, my J equation would be negative 6.24 plus 0.3 alpha CD equals, let's see, 10.8. And then here, the 1.5 alpha CB, 1.5 alpha CB, right? When I do a cross product, the first thing I do is I just take the numbers. I just take whatever's in front of the I's and J's and K's, and I go ahead and multiply those together. So that's where I've got the 1.5 alpha CB. And now I'm going to do the cross product. K cross I is positive J, so this is positive. I don't see any negatives anywhere. This is positive right here. All right, and so then I would plug this in right here, and I would get alpha CB. Alpha CB is, okay, and I'll fill that in just a second. All right. So you do have to finish this math, but let me recap, and let's take a step back and look at what we did. All right, I knew this was problem 4, but also when I see these links and I see something in pure rotation, but then when I see a bar that is not in pure rotation, I think to myself, okay, there's no kind of easy way to jump from maybe the velocity of B to the velocity of C. So I think to myself, okay, I kind of need a method, either the relative velocity method or the instantaneous center method, to kind of jump from the velocity of B, which I could find and I know pretty easily, 1.8, to, what is the velocity of C and the angular velocity of that bar. So that's kind of why, in addition to, obviously, it's problem number 4, that's why I knew I needed to use the relative velocity method or instantaneous center velocity method. Relative velocity method, it's on your formula sheet, sort of, but memorize that. VC equals VB plus VC slash B. VC slash B immediately rewrite as omega cross R C slash B. And R C slash B is from B to C. And then it's just a matter of plugging things in. Do I know VB? Yeah, I know VB completely because of the information that was given. It's -1 in the I. Do I know VC? I don't know the magnitude, but I know its direction because it's confined. It's confined to move right here tangential to this link right here. So plug those in, solve for the unknowns. Acceleration was a lot more tricky. All right, first of all, you've got 2 things over here for your relative term. And these, if they're normal tangential, I've got to not forget about normal acceleration in addition to tangential acceleration. Normal acceleration and tangential acceleration. So I took a side note. I looked just at link CD to find the normal and tangential acceleration of point C, which was 4 terms. All these 4 terms right here is just that left-hand side of the equation. Point B, we were lucky that it was a constant velocity, so no acceleration, and we were lucky that it was just at the very bottom of that wheel. So there was only 1 term for that one. Then plugged it in right here. Plugged everything in. Careful, this is a cross product. This is a multiplication. 2 equations, 2 unknowns. If you've got 2 unknowns, probably a good sign. If you don't have 2 unknowns, probably not a good sign. All right.